Hi all. In last module, we saw electric field intensity, electric flux density, Coulomb's law, and Gauss law and its applications. In module, it was completely concentrated on field and its density and laws applicable for electrical field. So now in this video, we'll start the second module, that is electric work, potential, energy, and the types of the conductors and materials. So in the first part of the second module, we will study the potential and energy in the electric field. So in this video, we are going to learn what is electrical work done and potential work difference at particular point. General term, if you use work done means you are moving some material or some parts of some material to some places. You are applying some force and moving it to some place to other place. So if you consider this picture here, a man is lifting weights. So he has to apply force to lift this weight because of gravitational force, the force applied naturally applied on that weights will be downwards. But the man has to put the force in opposite direction of that gravitational force to lift that. So when he lift the weights from the floor position to upper position, so then we can call the work done. Similarly, when we have the electric field around that, so when we want to move from charge from one place to other place, so at that time we want to apply a force. So to do that work, the work which is done in that case is called electrical work. So if you consider two charges here, so one charge with positive 1 nanocoulomb charge and other charge with again positive 1 nanocoulomb charge. I am considering this charge is producing a field around that. This charge, as we see in the last module, so this 1 coulomb charge will produce a field around that charge. So because of that charge, so when I bring this 1 coulomb charge near to this charge, there will be force acting between these two charges. There will be force acting between these two charges, right? So because of Coulomb's law, when there is a charge placed at a distance, the force acting between them is directly proportional to product of magnitude of charge and inversely proportional to square of distance between. So there will be force exists between two charges, right? So what is the force between these two charges? Here it will be repulsive force because both the charges are similar type, so there will be repulsive type of the force. So when I want to move this charge near to this charge, then I have to apply a force in opposite direction of the force exists between these two fields. Now what is the work done? So work done, we can term work done as it is a energy expended to move a charge from one place to other place in a electric field. It is a energy expended to move a charge from one place to other place is called electrical work done. So to do work, I need to apply a external force. To do a work, I need to apply a external force. The force, now what is the direction of, in this case, what is the direction of the force here? The force applied from this charge on this charge will be moving outside of this because it will be moving out away from this charge. So we have to apply a force such that my charge will move nearer to that. My charge will move nearer to this 1 coulomb charge. So force should be acting from external part. So it should be in the direction of this charge. So it should be in this direction. So it should be acting from here to here. So I have to apply a charge from here, this place to force from this place to this place to move my charge of 1 nanocoulomb to here, this place. So I have to apply a I have to apply a charge for that to do electrical work done. But what is the direction of the force? The direction of the external force applied will be opposite direction of force between that two charges, or we can say the applied force will be in the opposite direction of the opposite direction of electric field. Now, what is the external field I need to apply here is termed as what is the external force I need to apply at that particular point to move that charge, that is called as potential of that point. So what is the external force I need to apply at this point to move this charge from here to here, so that is called as potential of this point. Now what is the potential of particular point? It is a, simply if you tell the potential of the particular point, it is a the external force required to move a charge in a electric field. We can tell it is a potential of electric field. Similarly, we can define electrical work as it is a energy expended to move a charge against the electric field is called as electrical work done. Now, I told what is the potential at a particular point, or potential energy at a particular point. It is the external force we need to apply to move a charge against a field is called potential energy at a particular point. It is called as potential energy. Now we know that there is a different terms called potential energy. So what is these terms? We will see one by one. So next we will see what is, before going for potential difference. So we will see what is the expression for work done. Now, as I told, there is the force between these two charges. What is the direction of the force here? So we will see, taking one more example. If I see this diagram here, so I am placing a charge Q1. The charge Q1 is a unit positive charge. Here charge Q1 is a unit positive charge. It will produce a field around this charge. The field will be radially spread over the surface. So the field produced from this charge will be radially spread over the surface. So there will be field lines created around the charge Q1. The charge 1 has positively charged. Now I want to move the charge QT. I want to move the charge QT in this direction. I want to move the charge QT from here to here. So I want to move the charge QT from this position to this position for a length of dl. I want to move a charge, this test charge. I will take QT as a test charge. I want to move that charge from this position to this position for a length dl. I want to move a charge for a length dl. So what is the force? How we can find force between them? So force between them is written as the product of magnitude of charges divided by distance between them. The product of magnitude of charges, distance between them. But we don't know what is the distance between Q1 and QT. We don't know what is the distance between Q1 and QT. But we know what is the electric field produced from this Q1. So I want to determine what is the force between these two charges using electric field intensity and the distance. I can calculate using electric field intensity and the magnitude of charge. I can calculate the force, right? So we know that relation between force and electric field intensity is F is equal to Q into E. F is equal to Q into E. So we can also define electric field intensity is a force on a unit charge or force on a particular charge from other charge. We can define it as an electric field intensity. So as per Coulomb's law, we can write F is equal to the charge into electric field intensity produced from this Q1 into the test charge is equal to force between these two charges. It is a force between these two charges will written as QT into E. Now, so what is this direction of the charge will be? The direction of the force will acting between these two charges. The direction of the force between these two charges is in the direction of the line joining between these two charges. It will be along this line. So the unit vector along that line I will take as AL cap. So vector FL can be written as F dot AL cap. So F dot AL cap. It is a direction unit vector. So what is here? F. F is Qt into electric field intensity. F is Qt into electric field intensity. So substituting that, so you will get FL is equal to Qt into E into dot AL cap. Now I want to find what is the work done at this place to move Qt at a direction of dl. So I can write, and I want to now what is the work done. Now if I leave this charge as it is, if I leave this charge as it is, this charge will move at this direction, right? This charge will move at the direction of FL. So I want to make this charge as steady state. I don't want to move this charge to any position. So if I don't want to move this charge to in this position, any position, then what is the force I need to apply is, it should be in the opposite direction. It should be opposite direction of FL. Then only I can keep charge in a equilibrium position. So I have to apply a force in a opposite direction. So F applied should be equal to minus FL. So I can write minus Qt into E in dot AL cap. So minus Qt, it should be minus Qt E dot AL cap. It is a force applied. Now what is the work done here to keep charge in a same place, but here it was in dl, but I have to move the charge at a position of dl. Now what should be the work done? Work done can be written as force into distance traveled. So force into distance traveled will give me the work done. Now what is the force applied here? It is a minus FL. So what is the distance traveled? The distance traveled is dl. So I can write the work done, which is the elemental work done dw, which is equal to force applied into distance traveled. Force applied into distance traveled. So which is equal to minus Qt E dot AL cap into dl. Now what is this dl into AL cap can be written as dl vector. So dl into AL cap can be written as dl vector. So substituting here, this will be dw is equal to minus Qt into E dot dl is the elemental work done. Now what is the total work done? How we can find total work done? So elemental work done is the small volume of the work done. So to find total work done, so I have to integrate this expression for the path it is traveled. So from the charge, if it is traveled from here to here, then I have to integrate from this position to this position, starting position to final position. I have to integrate, and I can find what is the charge, what is the total work done over the path. So I can write the W, that is work done, which is equal to the integration over initial position to final position of dw. So what is dw? Dw is minus Qt into E dot dl. So what is the expression for work done is W is equal to minus Q, the integration from initial position to final position, E dot dl. So this is the expression for work done. So what is work done? Work done is the energy expended to move charge from one point to other point. So see here, this is the energy expended. This is a force into Q into E will be force into the distance traveled will be work done. So in next video we will see what is line integral and potential difference between two different points. Thank you.